This is a weird question to start with for Calculus 2. Presumably, you've been through a whole calculus class, and so presumably you would know what is calculus. Some of you have been in my class before and know what I'm about to say. Some of you have been in my class before and you're like, oh, dude, we know what calculus is. This is Calc 2. You just said that. But what I want to talk about is the framing and the story that's in Calc 2. I want to talk about the reason that we study calculus the way that we do, and I want to discuss the central tension in what's going on in the story of calculus. So let's talk about what is calculus the way that I see it. I see calculus as the study of infinity. In my view, we study calculus because this is our first foray into studying infinity. Now, when I say the study of infinity, I don't just mean do your research and like look for and Google stuff that agrees with you. That's what most people think of as research. And that's what most people think of as study. And that's, what's it called? Bullshit. So I think of calculus as the rigorous study of infinity. So like this is a math class. So we're going to have like epsilons and deltas, and we're going to think about what this means rigorously. So the rigorous. That means we got to follow rules. That means we have to use terms that are well defined, not your normal internet business. So I want to think of calculus as the study of infinity, the rigorous study of infinity. The way I see it, there's a central tension in calculus. The reason that we have so much trouble with this particular concept. The central tension in calculus is the difference between the countable and the uncountable, the discrete and the continuous. So our central tension in calculus is the conflict between the discrete and the continuous. The discrete that we can understand and the continuous that we have a really hard time quantifying. That's actually not true. We don't have a problem quantifying what's continuous. We have a problem crossing the boundary from the describing things discretely to thinking of things continuously. But this is our central tension. Thinking about the discrete versus the continuous. The countable versus the uncountable. The countable versus the uncountable. The difference between different kind of values. The number of students in this class is countable because we can count the number of students in this class. 1, 2, 3, 4, 5, and so on. We can assign each student in the class an integer. We cannot do that, for example, for a person's height. If at one day you are 5'2" and the next day you're 5'3", you were necessarily everything in between. You didn't skip any steps. You went continuously from one to the other. That's a continuous variable. And then infinity jumps up and says, hey, have I got some questions for you? So what is calculus? I think of calculus as the study of infinity, and our central tension is the conflict between the discrete and the continuous. Any questions? First TikTok down. Up second, the framing device. This is how we're going to tell the story of this central tension. Our framing device is our two big questions. This is how we're going to discuss our central tension. The two big questions of calculus: what is the slope of the line tangent to a curve at a given point? And what is the area under a curve and above an interval? So the two big questions: slope of the tangent line and area under the curve. I should specify that we want the slope of the tangent line at a point. This is going to be our derivative half of things. And the derivative is a local thing. And the area under the curve, which takes place over an interval. So the area under a curve and above an interval. I found that through my calculations, a picture is not worth 1,000 words, but it's worth quite a few. The idea is that we've got some kind of curve. We usually start with functions. We usually define our curves with functions because it's easier. This is the calculus version of no friction, no air resistance. It makes the problem easier to deal with. Like a joke in physics, we're like, oh, well, what if there is air resistance? I'm like, oh, that's fine. Let's do that. I want to make life more complicated too. I know this is only your first day in physics, but let's throw in friction. You don't want that. You're just trying to be edgy. So knock it off. So we want the slope of the line tangent to a curve at a given point. That means at a point, what's the slope of this line tangent to the curve? At this point, since it's Calc 2, we actually know this. It's the derivative at this point. The other big question of calculus is the area under a curve and above an interval. Once again, we start by looking at a function because functions are easier. And for whatever reason, we want to know the area under that curve. We may remember the answer to this question as well. This area is the definite integral from a to b of f of x dx. This is the framing device that we're going to use to discuss our central tension, the boundary between the discrete and the continuous, the countable and the uncountable, and where infinity plays in. I have more than 3 minutes. I have to cut that down. Any questions? The reason that you can tell that most calculus classes, or that calculus classes, calculus, the way you can tell that calculus is an engineering class, even though it says math right at the front of it. It's like, oh, I don't like math when you're talking about calculus. You can tell that this is an engineering class because for the most part, the first general description you get of what is calculus is people be like, it's the mathematics of change. And there's this focus on, this is the instantaneous rate of change. You know what? Let's just use the first instantaneous rate of change that we care about, instantaneous velocity. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. And then the calculus teacher's like, oh, this sounds like you're just trying to get us to teach your physics class for you. And then we turn around and physics is like, oh, gotta go to lab. And then they're like, oh, wait, we have questions. And they're like, oh, nope. And then the calculus teachers look around and say, oh, did they just trick us into teaching physics? Son of a. But anyway. Then we're like, well, now we got to talk about area under the curve. And then the physicists be outside the door. It's like, oh, you know, you should make that distance and make the graph velocity. I'm like, oh, come back here. We have questions. And they're like, oh, got to go to lab. Son of a. But there's revenge, right? Because in the afternoon, you look for a physics instructor as a math instructor. It's like, oh, hey, where are you off to? You're like, oh, got to go to lab. It's like, oh, I got to go home. I'm just kidding. I would never flip off my physics college. For those of you watching at home, I just like casually flipped off the person that I was supposedly walking away from. I would never actually do that to my physics college. Even though they make me teach their class. I'm just kidding. It's not like that at all. All right, so we've talked about our central tension. We've talked about our framing device. We've got to talk about how we think of these things from a mathematical perspective. Yeah, we are going to use physics. There's even some applications where it's like, oh, hey, business is a calculus too. And I'm like, oh, fine. And it's economics. But we get distracted by all of these applications of calculus. And it distracts us from the whole point. And so this is why this class from me is such a disaster. Because I'm like, oh, I'm going to teach calculus as a math subject. And you're like, oh, well, isn't it a math subject? Well, yeah, but when you're engineers, you don't really care about why things work. You just want things that work. So I'm like, oh, let's talk about how this area stuff works. And I'm like, oh, son of a bitch, just tell me the fundamental theorem of calculus so that I can take all this stuff to Wolfram Alpha and finish this class. You know what I mean? Everybody heard of Wolfram Alpha, right? It'd be really weird at this point in your career if you haven't. It's like, maybe it's like something wrong. So there's our central tension. There's our framing device, number 3. How do we use our framing device to explore the central tension? How are we going to use this framing device? So let's actually label that. How do we use the framing device? What did we use? In the case of the tangent line, we approximate the tangent line with the slope of the secant line. So in first category, we approximate the tangent line with the secant line. This is what we normally lead with in Calc 1. If we looked at the two framing devices and said one is clearly easier than the other one, let's start with the messy one first. But we're looking for the slope of a line The problem is we only know 1 point. And everything that we learned about slope the slope is a rise over run, the change in the y divided by the change in x. If we want to know how much something has changed, we got to subtract. We need 2 points. So we approximate our tangent line with a secant line. By grabbing a second point, and we approximate the tangent line by grabbing a second point from the function and saying this slope of the secant line is close to the slope of the tangent line. Then we do the calculus thing. We improve the approximation by taking that second point and moving it closer to the first point. Because the closer those 2 points are, the closer our secant line will approximate the tangent line. That's how we improve the approximation. Every time you want to approximate something, you've got to figure out how you can make your approximation better. And this is what we're going to do. And then this is where calculus jumps in. If closer makes the approximation better, we want to make these 2 points infinitely close together. That's the calculus way. So calculus says, now just make them infinitely close together. Not exactly the same. We can't do that. We can't have delta y over delta x be like 0 over 0. That's not defined. We just want it to be close to 0 divided by close to 0. So the question becomes, how close? Infinitely close. That's the calculus way. Take that thing you're doing to improve the approximation and do it infinite. When we have 2 points, we've got this distinct delta y over delta x. When we've got 1 point, we've got 0 over 0. We're looking for what happens in between. We're looking for what's going on. How do we read what's going on? Because our central tension is the difference between this discrete, this countable, and this continuous. Somewhere in, this is not the continuous one. I'm not pointing at the two things here. But when we have 2 points, we got a delta y over delta x. We only have 1 point, that's 0 over 0. We got to figure out what we want in the middle. So this is how the framing device uses, how infinity shows up in our framing device for that first part. In the second part, we approximate the area under the curve with the only area equation, area formula that we need. Area is length times width. The reason that we can't just say length times width is that the length is not only variable, the length is continuously variable. What a pain. Not only variable, but continuously variable. This, as a sidebar, this is the only application of integration that we need. Area is equal to length times width. Every other application is just derivative of this. I know this is the integral side of things. I mean, like derivative. All we need is area is equal to length times width. Now all of our applications of integration are just our applications of multiplication. People be asking, what do we use integration for? The snotty response is now, I don't know. What do we use multiplication for? Now, if you're going to do that, you got to make sure that you have that snarky attitude that's really annoying, because that will turn people off from asking you questions. I'm starting to wonder if maybe this is why people don't like math, but how do we not be snarky? I figure at this point, you're already in a Calculus 2 class anyway. You're committed. Some time fallacy is going to show up. And I go, well, I'm stuck here anyway. You know what I mean? But got to make sure it has that snarky edge. Because the applications of integration are just applications of multiplication. Area is equal to length times width. That's the one that we're going to be using here. Distance is equal to rate times time. That's the one that the physics department called and said we have to use. But anywhere we have multiplication, we can have an applications of integration. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. Running this backwards, since we can't use multiplication if one of our factors is variable, we have to drop it back to where multiplication comes from. This means that integration is addition. because we have to use addition instead of multiplication if all of our stuff is variable. Multiplication is just addition when everything's the same. Any questions? So was that 3 or was that 4? Central tension, number 1. Number 2, framing device. Number 3, how do we use the framing device? I think that one comes in 2 parts. I think I talk a lot about approximating the tangent line with the secant line. And so I think a 4th one should be area is equal to length times width, but the length is continuously variable. And that 4th one will serve as an introduction to the next several weeks. Any questions? Comment? Snide remarks? Of course not. It's 9 o'clock. No one's going to have a question now. Everybody's been mad at you. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day. And I forgot to take roll. And thanks for playing.